WITS, there was, when I started at WITS, there were no information engineering. So it was just a straight BSc electrical engineering degree. And we did a few IT courses, one in second year where we had to learn Pascal. That gives you an idea of how old I am. And then in fourth year, there was electives that you could use. And I had no intention of going into the IT industry at that stage, so I didn't choose any of the electives. And it just so happened, I started working as a software engineer in my working life. And I noticed that when I started working with computer scientists, there was large gaps in my knowledge. So WITS at that stage offered a part-time higher diploma in computer science, where if you had a previous degree, like a pure mathematics degree or an engineering degree, you didn't have to do the other aspects of your computer science degree. You just focused on the computer science subjects, and that was called the higher diploma in computer science, which I completed part-time at WITS. And then obviously later in my life, I completed my master's in computer engineering and my PhD in computer engineering at the University of Pretoria. I just want to emphasize that I am not a data scientist. So my research previously and currently has been in wireless sensor networks, which today is called the Internet of Things. So these are sensors that, tiny sensors that you place in the environment, wearable technology, and you have to do research on how you're going to ensure that they stay alive for as long as possible, because they're not connected to an electrical source. So you want to ensure that the way you send messages or route these messages are optimized to conserve energy, and to ensure how to ensure that, since it's wireless communication, how that the messages actually reach a source where it can be collected and stored. So it was a lot of computer networks and integration systems. And recently I've looked at augmented reality. And currently I've rejoined UJ because I want to focus on research in practical medical applications. So I want to emphasize I'm not a data scientist. Most of you all know more data science concepts than me. So why am I here? Okay, when I saw the winter school, so I'll be totally honest, when I saw the winter school, initially, I thought, okay, it would be nice for me to learn, because there's certain aspects of my current research where I need data science type students. And it would be good for me to learn, because it's difficult to supervise a student if you don't understand the underlying concepts yourself. And the students I'm looking for currently, it's difficult to find students in the pure engineering field, because my research is the intersection of programming and electronics. And to give you an idea, our primary language of programming is in C, because it's microprocessors, so it's not Python. But we need some sort of a student who is more interested in data science, because there's certain aspects of our research which requires more of the data science and machine learning. And so I'm hoping that today, with my presentation, some of you would consider, instead of doing a pure computer science or data science postgraduate study, you might consider doing it more in the engineering field, where you can still apply some of your data science concepts, but for more engineering type application. So I've posted my email address in the chat group, and if you're interested in pursuing that. So that's one of the reasons why I decided, okay, maybe I should, because I initially wanted to just join the winter school to learn more, as I said. And then when I was asked to present, it was like, maybe I should just tell them I'm not a data scientist. But then I thought, if I could use it as an opportunity to engage with everyone and and hopefully get people to, join me in my research, then I should just present. And so that's what I'm going to do. So I hope you understand. I've been honest. It's not going to be like the previous 4 presentations where they were solid data scientists. I'm more of an engineering background. So I hope you'll bear with me. So I'd like to start off because, like I said, I'm quite old, and I've just come back into academia from the corporate world. Is that if you don't have the historical context of what's happening, okay, with the current IT systems, you're going to struggle. I've noticed with the younger generation, if they don't have that historical context, then they not always understand why certain systems, a lot of the systems in the corporate environment is legacy systems, and why they were put in place there. It's because that was the technology that existed at that stage. And today's technology is obviously new, and it can do so much more than the old technology. But that was the technology that existed, and that's why it was used. So I'm going to start off by talking about the history of data and information, the original databases, and out of that, how it led to what is now currently regarded as the cloud. Okay, so to understand why we currently have this technology concept known as the cloud, we actually have to look at how humans and corporations, organizations have evolved in their use and storage of data. Okay, so obviously data was initially stored in physical files. Okay, so it was handwritten or typewritten files. Okay, that was stored in paper-based. Then came computers, and the go-to technique for storage changed to flat file databases. So the original ideas for a relational database management system, that was more than 60 years ago. It was in the 1960s when they started developing multi-value databases, okay, and hierarchical databases. And then these databases have complex mathematical logic, and they didn't really have what we regard today as a relatively easy standard query language, which is SQL for relational type databases. It required complex mathematical logic. So I've put there a little cartoon kind of picture to explain to, I'm assuming my audience is all in their 20s or early 30s. So you might not have realized that the original phones, okay, were fixed line phones, okay, and now we have wireless type phones. And you can already see just in something as modern as cellular telephony, how rapidly the technology has evolved in this field. So database and information storage is actually much older than this, and we can see that it's got a long history, okay? And if you understand the history, then you can understand the cloud. So the original relational database and a new query language was created at IBM Research in the early 1970s. So this is standard query language, okay, SQL. It was more accessible to users without formal training in mathematics or computer programming. IBM also developed their database manager, which uses hashing techniques to provide faster retrieval of data. So Database Manager supports atomic transactions, okay? So that's atomicity, consistency, isolation, and durability. So it means that an update to data will occur if all processes are completed, or it will just roll back. So it has to be atomic. It has to be consistent because you're talking about transactions. It has to be isolated, so it does not interfere with any other transactions, and it must be durable. Now, it's important to understand IBM at this stage was the leading computer vendor. Their focus in their specialization was on these large computers, typically known as mainframe computers, and they're still currently the main manufacturer of these large mainframe computers. They're not so large anymore, but it's derived significant revenue. So their research, they have an internal research department. They were saying, okay, we're interacting with these corporations, and they using our large mainframe computers to store their data. And now they want to analyze this data, okay, and generate reports. So they require a database manager to store the data and then to, analyze it using this query language. So they spent significant research effort in developing this database manager in SQL, because it provided direct benefit to their business and the needs of their consumers during that stage in corporate life. So it was mainly big banks and large corporations that just wanted to store their data. And they said, if it's stored in a central large computer, that's perfectly acceptable. So over the next few decades, as SQL popularity increased, there was other companies that developed relational databases. Okay, so you had Ingress DB2, Oracle, and then there was open source databases such as MySQL. Okay, so you can see that the history of the database. Now you'll notice that in around the mid-1990s, there was open source databases such as MySQL, and then in the early 2000s, there was new novel databases that came along, such as MongoDB and Hadoop. Okay. So if you think about SQL, SQL is the current for relational type databases. It's the current language for interacting with the databases. And these legacy information databases were very large. And if you needed to increase the amount of data storage, okay, you just increase the size of your computer. So it was typically stored, like I said, on mainframe computers, or if it was on a server, it was just, you increase the size of your server, your hardware storage capability. So it was one central machine, okay? It wasn't a distributed machines. So it was one central machine that stored it. And if you want to have a disaster recovery in place, in case anything happened to this machine, you had an identical machine, okay, an identical mainframe or a rack of servers that you stored in a different location, and you copied the data from one, the current in-system operational database to the backup database, generally as a batch process overnight, and you stored it to for disaster recovery purposes in large corporations. But it was all a centralized large machines. That's what I'm trying to convey to you. it was not distributed technology that currently, as we understand, with internet and with cloud. So the relational model and SQL were invented at a time when data management targeted primarily administrative applications, which was exemplified by banking, where you had accounts, customers, and you had transactions. And these transactions, as I've said prior, is asset type transactions. So it needs to be, it's completed once all processes are completed or that update is rolled back. Okay, so you don't want two different values stored in any place in your data. Okay, it's all completed or it's rolled back. So the relational model in SQL are well suited for managing this kind of data and supporting workloads made of these kinds of transactions. So you can see also the same way previously, databases, the hardware and the actual database manager evolved. So the query language also evolved at the same time. Okay. And this query language was specifically for relational type databases. Now, these databases, if you look at how they behave, they actually have a large amount of overhead that is not useful work. So they have to, because they have to adhere to strong asset requirements, okay, that atomicity, consistency, isolation, and durability requirements, they actually have to lock. So if they're currently updating data, they have to lock that all aspects of their database, okay? So they can't do multiple transactions at the same time, okay? They have to log so that they can keep records, okay, of what's happening. And they have to then buffer all these incoming transaction requests. So they have a very small amount of useful work on that machine resources that's actually dedicated to the task at hand. So basically, as I said, atomicity, means an update is performed completely or not at all. Consistency means no part of a transaction will be allowed to break a database's rules. Isolation means each application runs transactions independently of other applications operating currently, and durability means that completed transactions will persist. So having to perform these restraints on every piece of data makes relational databases slower. Now, in the 1990s, okay, as the internet grew, so the internet, for those of you who've who've studied the history of the internet, it was actually ARPANET. It was created from research universities, originally as part of the defense, DARPA. And then these universities created the ARPANET. And as this research grew, it eventually, the internet grew out of this. It became more of a business networking capability. And in the mid to late 1990s, it evolved from these universities in the States to universities around the world, and then to corporations towards the late 1990s. Corporations started saying, okay, maybe we can do something with the internet. And that's when the terms like e-commerce started being used. But it was still static websites, okay, not the current dynamic websites we're familiar with. And it was just a mechanism to have a web page where you display some data. So that was the original. And the underlying networking protocols were also still evolving at that stage, because at that stage, they were not designed to handle the large volumes of traffic that we currently experience. And seamlessly in the background, we send large volumes of data. And these underlying networking protocols can handle this large volume of data without, significant user problems. So as a user, do not experience significant delays or backlogs in your between a request and a response. So it's relatively fast, but that was still evolving at that stage in the 1990s. So the same thing that was happening with networking technologies and the hardware was also evolving within the information sphere. So in the 1990s, the initial NoSQL databases, okay, because the original data, the relational databases were meant with large corporations existing that wanted to store very structured type of information. So it was banks, and large corporations that wanted to store their accounting and transactional information. Now, as the internet grew, these companies that started engaging in early e-commerce, and they just wanted to store all their customer information that they could later analyze. And they were not that concerned with the consistency, because they're not involved in a bank transaction, okay, where consistency is important. They just wanted to keep the data and then later go back and analyze it to improve their service that they were offering to their customers. So they were becoming more customer-centric and trying to get as much data about their clients as possible so they could analyze it and improve the service they offer to the clients. And these were small startups. They were not necessarily these large, well-financed organizations which could afford to invest in expensive mainframe computers. And at that stage, relational databases, and even today, relational databases are very expensive, okay? So relational databases are designed to run on a single expensive machine, and as they're required to scale, more expensive machines are required. So these internet companies wanted to just use existing computers that they could buy in a store that was cheap. So cheaper commodity hardware to store data. And then they could connect multiple of these cheap computers together, okay, on a local network to store their data. So that was NoSQL databases. They were data stores designed to scale horizontally, okay, and use a cluster of cheap commodity hardware to store data. So even if one of these computers in a cluster fails, okay, you could still use the remaining computers, okay, to store the data. So the way they were inbuilt, okay, to say, okay, I need to write to this computer is not available, I'll try the next computer and send my data there to store the data. So their overall cluster reliability was quite high, and they were designed, whereas relational databases had to write to a central server, and if that server was down, you couldn't write, and the entire system collapsed. So the availability of the system it was extremely low, because if there was a failure at one point, it was no longer available. Whereas with a cluster of low-cost machines in the NoSQL environment, if you had many people accessing a web page and interacting on that web page, And if one of the servers, the computer machines was down, you could use another similar cheap machine to store the information. Okay, so the availability suddenly became quite high. And these NoSQL data stores, they were designed to scale, to have high availability, and also they were not necessarily relational. So it was like, if I want to store information, I don't need to invest a lot of time drawing up table schemas and understanding relationships. I'll just store the data and later I'll analyze it and decide how I'm going to restructure this data. So you're just storing it. So NoSQL you didn't have to spend a lot of time designing your database schema and the relationships. So with the advent of social networking sites like Facebook and Twitter, the demand for new technology that could handle large amounts of data increased. So the initial companies that were at the forefront of the internet, okay, and were storing large amounts of data. So if you think about it, in the 1990s, working in the corporate environment at that stage, and it must have been around 1996 or 1997, I started using Google, okay, as the search engine of that I preferred. And because at that stage, people were still looking at other types of search engines that they were using. And I started using Google. So it was still a young company in the 1990s. And they were storing data about how people, the types of search requests people were requesting. And they were creating their, scanning all these web pages and creating data so that they could improve their search engine. And they developed the initial database, MapReduce and Bigtable. And Amazon also started off in the 1990s as a bookstore, an online bookstore, an e-commerce to buy books. At that stage, it wasn't electronic books. You still got books delivered to your home and as paper-based books. And they were also collecting information about their clients. So they developed their own distributed. It's important to understand distributed is not at the central place. It's no longer centralized, placed on a single hardware. Okay, it's now placed on different hardware distributed across data centers, non-relational systems, okay, to store all this data, because the company saw this need to store this data quickly without having to spend a lot of time trying to understand the database schema you need to, from a relational perspective, and to use cheap hardware, okay? So they created, were researchers at these companies. They created MapReduce, Bigtable, and Dynamo. So these papers, okay, eventually led to the emergence of even more non-relational databases. So you'll notice that in the IT, there's generally one company, they might do some research and they might invent something, and then eventually they, they make it out as an open source technology that's available to the broader community. And perhaps one or two of the original developers of that might join this new company, and then they'll start off as an open source project where they market it. So that's how Hadoop was created. It was based on the MapReduce paper. Cassandra was on the Bigtable and Dynamo papers, and MongoDB. So these are the NoSQL type. Mongo is, NoSQL type databases. Now, these databases were largely written from scratch. They also did not use SQL, leading to the rise of the NoSQL movement. And these databases are much faster than relational databases because they don't need to do all the locking and the latching and the buffering that traditional relational databases, which are have to strictly adhere to ACID requirements. So they are easier to scale horizontally because the data is distributed and managed by different machines. While relational database systems were initially proposed to store and manage structured data, NoSQL databases were designed to deal with very large volumes of data. Okay. So you need a distributed system where you have the high availability. So if one machine is down, you can still store the data on another machine. And you have large volumes of data. So a traditional system, if you suddenly notice that your incoming data volumes are increasing, it's actually having to switch the machine off, add more hard disk space, and then restart the machine, and then you can consume the volumes, the increased volumes. But this is not viable in a real-time networked world where you have this constant stream of data coming in, and you don't have the luxury of being able to switch off your machines and upgrade and then restart. So you need to be able to deal with the stream of data that's coming in continuously without there being any hitch or a stopping process. And if you have a distributed system, a network system, you can send the data to those machines that are currently available and bring online new computers, okay, to handle the increased volume. So you're scaling horizontally, okay? You're not scaling one single machine better with better hardware or more hardware. So you're not scaling up vertically, you're scaling horizontally. So relational database systems are usually scaled up, move to a larger and more powerful servers. NoSQL database systems are designed to scale out. The database is distributed across multiple hosts as the load increases. This is more in line with real-time web traffic as transaction rates and availability requirements increase and as data stores move into the cloud. So if you look here, you'll see the history. So in the early 1990s, it was business transaction data. But as data grew with the advent of the internet, okay, you had much more web application data. So your business transaction data also grew, but it did not grow as exponentially as your web application data. So to handle this, you needed to have these NoSQL database systems, okay, so they can easily scale out using low-cost commodity processes to yield economic advantages. And today, NoSQL databases such as CouchDB, MongoDB, Cassandra, and HBase have emerged as a way to store unstructured data and other complex objects such as documents, data streams, and graphs. So this is part of the evolution of database and information systems. So NoSQL databases provide flexibility, addition or deletion of an attribute from data because they have a fixed database schema. Now, if a fixed database schema, you suddenly want to add another row, not another row, another column. Okay, so you've got your schema and you need to add in an additional column. It's going to have an impact because historically all the, okay. So NoSQL databases, if they JSON type files, they store information traditionally as JSON type files. And here you could just add a new data element, okay? And assign it a value with no impact on your database schema or the time. So you could change very rapidly what information is stored, because they store data in JSON format. So there's no requirements for the traditional database schema and your data model. So depending on the requirements of the application, we can use different types of NoSQL database, and each NoSQL database has its own features, data model, and architecture. Choice of the database depends on the application. So NoSQL databases have a loosely defined set of characteristics and properties. They can scale horizontally with the addition of new servers. Data replication and distribution over multiple servers is used for coping with failure and achieving eventual consistency. So what is eventual consistency? This is a weaker form of concurrency than ACID transactions, which does not lock a piece of data, but uses data replication over multiple servers to cope with conflicts. So it means that eventually all the data will be consistent, as the name implies. So if someone needs to read the data, and on one server you're currently writing a new version of their data, the user might read data that is temporarily inconsistent with what is currently being written. So you might read a value of 10, and that value of 10 is currently being overwritten with a value of 15. So you'll see that. But if you go and check 10 minutes later, when the data between the initial server that was overwritten with the 15 is then propagated to all the other servers in that distributed database system, it will all eventually be at 15. So if you go 10 minutes later and read that same block of data, it will return the value of 15. So it will eventually become consistent, okay? Whereas with ACID type transactions, it's like you store it once and you cannot read while you're writing to that data. So as I explained, in the age of prior to the internet, when it made sense and it was acceptable to be able to do this where you're writing and you're unable to read because people didn't, it wasn't a requirement. But in the age of the internet, where people were wanting to access information, if you were overwriting that information and people wanted to access it, it was, does it make sense to stop people from reading this data until I ensure that all the database systems have that same value? Or should I just show them this data that's currently there on the assumption that eventually this data will be consistent? And because these companies, these internet companies were looking at the client experience and the real-time requirements for their client, they adopted the eventual consistency model for data transactions. Okay. They have simple interfaces. So these NoSQL databases have simple interfaces for searching the data and calling procedures. They use distributed indexes to store key data values for efficient searching. And the ability to add new fields is, to records is dynamic. You don't have a fixed schema. So these NoSQL databases also use the CAP theorem, okay? So it says, the CAP theorem says you can have 3 out of consistency, availability, and partition tolerance. So generally, in a distributed system, you want to be able to partition your data. So you want to store not in a large centralized space, but you want to store your data across multiple they're actually like servers, and you want to have them readily available. So you can out of these three principles, you can only have two out of these three. So most popular NoSQL databases chose to sacrifice consistency. So we said we will eventually become consistent. So they're not, unlike banking, so they do not need to ensure that consistency. So eventually the data will become consistent. So NoSQL are basically, their approach is, instead of ACID type transactions, they're saying they are basically available, soft state, and eventually consistent. So the base method defines this approach. Now, as I explained, the evolution, okay, so of databases, it doesn't mean that NoSQL databases are the best and a huge improvement. The reasons we had relational databases in structured query language is they were actually useful. So they are advantages in relational database systems and SQL. And as the internet companies through web applications were collecting this large amounts of data, once they needed to start analyzing this data. So initially, NoSQL databases, no fixed schema, the adaptability, the high availability, it made sense to store data in NoSQL databases. But once you wanted to analyze this data and do something with it, so you suddenly missed your SQL queries, because SQL is so efficient. It's a structured query language. You know, it's so beautiful in how you can create a SQL query to request information from a large database. And the analysts, you know, struggled with these NoSQL systems where data was just stored in a haphazard manner without any underlying mechanism to query it and to have joins, etc. So these NoSQL systems lack many traditional database features that application developers rely on, which is a robust query language. So developers have to write complex code to process and aggregate their data in their applications. So NoSQL methods are useful in simple retrieval scenarios. The SQL provides additional value in expressing more complex data access patterns and pushing computation to the data. Each NoSQL database had its own unique query language. The immaturity, so it was, you know, mid-1990s, early 2000s of these languages means more complexity at the application level. So this resulted in SQL interfaces on top of these newer databases. So on top of Hadoop, and the rise of NewSQL, which are scalable databases that fully embrace SQL. So you have currently NewSQL type databases. So they're trying to merge the best out of the old relational database systems and the NoSQL databases and create better databases, which is a more distributed type SQL database. So Google has created a geo-replicated SQL interface database, okay, based on their Spanner paper in 2012. And then you have CockroachDB database in 2014. And existing database communities, okay, have begun to adapt, okay, for their own survival and created different features on their databases, such as the PostgreSQL, okay, to incorporate some of these ideas from the NoSQL and the NewSQL movement. Okay, so we're going into a world where we're going to have increasingly more of a distributed type database systems, which will incorporate certain aspects of relational and NoSQL features. And it's going to offer, I think, the duality of having a structured query language for your for developers, as well as the ability, if you want, to have flexibility in not having a fixed schema, a fixed database schema. So databases are still evolving as we speak. So this briefly shows the current state of the databases. You have your relational, you have relational sharding, you have NoSQL, and then you have your current NewSQL type databases. So I've talked about now these relational databases, NoSQL databases, NewSQL databases, and the history of the SQL kind of language. And all of this is to manage data. So even today, the data storage and data management landscape is evolving. And today's landscape of data management applications is much more diverse than it was when the relational model and SQL were born. So we have different types of data today. We have semi-structured data, unstructured data, continuous data, which comes in a continuous stream of information, sensor data. We've increasingly, a lot of people have mentioned in this week's about the Internet of Things. So we're having sensors placed everywhere, okay? And all that information needs to go to a place where it can be analyzed. So you have sensor data, you have streaming data. So every time you watch movies or stream in videos from YouTube or Netflix or all this, that's continuous data that they're analyzing how you're behaving. Our current systems, we're using Zoom, etc. All this is data that's being collected by these companies to try to improve services they offer their clients, because they cannot stay static. Their competitors are, well, you know, in today's world, your competitors will each of you just have a product offering and you don't evolve that product offering. And the only way you can evolve that product offering is to improve it, is by collecting data on how it's being used, and then try to analyze the data to say, okay, this is how our clients are currently using this product, and how do we improve it to improve the experience of the clients so they'll stick to using this product. And so data is coming through to companies in multiple formats. Okay, you have graph data and other complex structured data. Similar diversities can be found in the workload supported today. So you have large amounts of data gathered from various sources in this cloud and storing this data into large databases. As different databases evolve for specific application requirements, it is better to build systems based on the nature of that application and its work data load. The volume of data is increasing at an enormous rate, and the cost associated with scaling a relational database management system is very expensive. In addition to storing gigabytes to terabytes of incoming streams of data, there is a need for high-speed transactional access to compute responses and analytics in real time, and not post-hoc in batch processing. So you need to be able to store increasing amounts of data, okay? And that's costly because storage is costly. It's not for free, you know, even with the the commoditization of hard drives, it still costs money. So these databases and methods of collecting data are perfect fit for scalable, elastic, cloud-hosted service. It provides customers with access to data that would have been impossible or impractical to gather or host within a legacy IT environment. And when this data is processed through analytical tools, it provides business intelligence that organizations have never had in such a useful form until now. So if you look at this picture, so this is where the term big data evolved from. Initially, we had data that was for corporate specific, that enterprise information, then they had customer information. So, and then you had the web, okay? And then you had all this other information. Suddenly you have sensors, social interactions, location data, okay? You have audio, video, speech to text, all this other information suddenly you need to store, and this complexity of the data is increasing. So you need to say, how do you store this data? So this data, just as new databases evolved to meet the needs of companies in the internet age, new networking and computing infrastructure evolved also to cope with the increasing data and storage requirements. So you initially had your mainframe computers, then you had the initial web, which was just client server technology. You still used a relational database, okay? Then you had relational databases, NoSQL, NewSQL, and big data platforms. And this is where you're using increasingly other forms of storing this data. So we're going from, terminals to access these mainframe applications. And then we had our desktop applications. Then we have our client servers as the data requirements changed. Then the initial internet, okay? You had multiple distributed servers. And as the internet evolved, internet applications became more dynamic from static web pages. You had high density service farms, and now you have more cloud enabled applications, okay, where you have software defined networks, okay, to support these cloud enabled applications. So databases have evolved, okay, to cloud computing. So technology has seen rapid evolution since the 1960s, from mainframes to cloud computing and beyond. So if you look at it, the first commercial computer, then we had mainframes, then we had desktops, portable computers, what we all using now currently are laptops. Nobody has a desktop computer, although I have one in my office. But, most, we in the age of tablets and laptops, okay? Then Amazon said, okay, we are this large internet company. So initially they had their servers. So they had their high density server farms, okay, to store their data. And they needed to manage this. So they had a whole team of people, okay, IT specialists, to say, how do we create this network of server farms to ensure high availability, scalability, reliability. And then they said, if we're struggling and we've created these processes and these technologies and these scripts to handle our networks and our server farms, we have all this as parts of our additional networking and server capacity that we require sometimes, but not all the time. So we actually investing in capital expenditure upfront on this hardware, on the assumption that the possibility might exist that in the future, our needs might require us to to store more information. But currently it's just sitting there, not being utilized. And since their philosophy was to utilize everything optimally, they said, okay, if we are not utilizing these resources, they're costing us money and they're sitting there, maybe we can outsource them to other companies and they can use it while we're not using it. So that's how AWS, Amazon Web Services, was launched. And this was the first kind of cloud-based company. And then Google and Microsoft followed later. And IBM also started its cloud-based, but it's since, left the cloud and it's more on the software and the applications that it can host on different cloud vendors. But these were all companies. So the cloud evolved from companies such as Amazon that were handling their own database requirements and needs with these large server farms and saying, okay, our spare networking and hardware capacity, it's just sitting there. How do we optimally utilize this? And the initial ideas was, there were also independent data center providers who tried to offer cloud, but the cloud evolved primarily from these large internet companies that were already handling in-house their own systems and said, okay, we've developed this capability. How do we commercialize this capability to bring in more revenue for ourselves? And that's how Google and AWS was launched, and Microsoft said they need to compete in this environment because they were initially just selling the software for servers and networks, and they needed to compete. So then they also launched their cloud-based business. Okay, so the National Institute of Standards and Technology gives the standard definition of cloud is, cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, such as networks, servers, storage applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. So currently, cloud computing is regarded as, it incorporates, content distribution networks, edge computing. So you have sensors at the edge that then uploads the data. You have X stands for anything, so it can be infrastructure as a service, software as a service, multiple aspects. So it could be anything as a service. You have distributed systems, and you can also have machine learning, because all this data, the big data that we collecting, it's optimized to be used on these distributed systems, and that is part of it. The vendors who operate these distributed systems can enable these machine learning algorithms. So Google has always been at the forefront of artificial intelligence research, as part of their business improvement. Amazon on how to analyze customers' buying habits so that they could buy more, So they were all part of that initial artificial intelligence and data analytics movement. And they've created these machine learning platforms incorporated it into their cloud computing service offerings, and businesses can now utilize it. So instead of having multiple open source platforms, it's all in a centralized cloud vendor space. So this is, I'm going to briefly talk about cloud computing, okay, and give you just a very quick overview of it. It's not at all sufficient what I'm going to discuss, and you're welcome. I'll post some information during our break, which we'll have in a few minutes, on a web page that you can go and learn more about cloud computing. But this is just going to be a very brief overview on cloud computing. So the cloud computing paradigm has emerged as an energy efficient, fault tolerant, and on-demand approach, which enables ubiquitous network access to a shared pool of flexibly reconfigurable computing resources. So it's basically your server farms, okay, with high-speed network access, okay, and they have these duplicate servers, okay, so that they can ensure that high availability, reliability, and they're using, trying to, you know, if one of the hardware servers fails, okay, they can rapidly start a new server. Okay, they just automated the process to say, okay, another server comes online, and then an alarm gets sounded, and the technician in that data center will just go and replace that hardware with another piece of hardware until it can be fixed, and it's very efficient. So you just bring up another system as soon as it's almost autonomous. These monitoring tools that will constantly monitor the hardware and the systems and say, okay, something has failed. So it will send through this ping all these servers, and if it does not get a response within a predefined time, it will say, okay, this server might potentially be down. Let me start up another server, and it will have all the pre-configurable applications it needs already on that server, and it will start up all these applications. So it could take over the job that that server that's no longer reachable was doing, with minimum impact on the performance of the entire system. So the client sees no performance impact from their point of view. Okay, so in the future, we do not compute on local computers. So if you think about it, we're actually going back into the future. So, you know, if you look at this picture, all the computation was done on the mainframe. Okay, so that was in the past. And then we had our desktops, and lots of computation was done on our desktop application. And then we had client server type applications. With some of it, we had then the concept of thin client and fat client. So determining on whether it was thin or fat, how much computation happened here and how much computation happened there. But now we're looking at a future where most of the computation will be done, okay, in the cloud. Okay, so they're done on facilities operated by third-party vendors. Okay, so these are factories for IT services at scale. So we load our data, and then we ask the different services available on the cloud to analyze their data, and we run it in the cloud, and then we just view the results of their data. So we just have an interface to the cloud. So cloud computing refers to both the applications delivered as services over the internet and the hardware and system software in the data centers that provide these services. So the data center hardware and software, not just the hardware. Prior, it used to be, okay, you might outsource your hardware to an external vendor, but you still retain control of the software. But now increasingly, the hardware and the software is outsourced, and this is what we call the cloud. So there's essential characteristics as defined by the NIST, okay? So it says there are 3 service models: software as a service, platform as a service, and infrastructure as a service. The NIST defines 4 deployment models: public, private, hybrid, and community clouds. So community clouds is a very specific type, with a group of companies or individuals who have specific focus, and they want to create their own cloud environment. They can, but generally, when people talk of the cloud deployment models, it could be either public, private, or hybrid, and that's what we're going to focus on. We're not going to focus on this 4th one in the rest of this talk. So the cloud models, you have a public cloud, which is owned by your cloud service provider, okay? So this is your Google, your Azure, your Microsoft Azure, your AWS. It provides resources and services to multiple organizations and users to connect to this cloud service, okay, via secure network connection, okay? You have no capital expenditure, so you don't have to buy a new server to scale up. It's very agile, so your applications can be made quickly accessible and deprovisioned whenever needed. And it's consumption-based model, so organizations pay only use and operate on an OpEx model. Now, so if you look at the evolution of commercial enterprises, we had these large corporations in the era of IBM, and then you had the initial internet companies such as, which was focused on either search engines such as Google, or the initial e-commerce type companies such as Amazon, which sold things. But they were also still had to invest. So they needed startup capital requirements and investors to, buy the equipment. They needed to buy the actual hardware. Now it's becoming easier for startups to say, okay, we don't need to invest a lot upfront in hardware. Okay, we'll just use, so there's no large initial capital expenditure. We'll try develop our service offering, and then as we scale up, we'll use an external vendor, and based on our use, that's how much we're going to pay. So that's an operational expense, and it means that you don't need a lot of money to start a company offering a service to consumers, because as your client base increases, obviously the revenue flowing in will increase. So you can pay for increasing service requirements to your cloud vendor. Okay, so that because your increasing revenue will pay for that operational expense. Now, so there's lots of benefit from the public cloud because you don't have any initial. Now, if you're a large corporation, you already own data centers. So a lot of these large corporations have their own data centers, which are fully or partially managed either by the company or a specific vendor that has a relationship with that company, an IT vendor that has a relationship with that company. So the private cloud is owned and operated by the organization that uses the resources from their cloud. They create a cloud environment in their own data center and provide self-service access to compute resources to users within their organization. The organization remains the owner, entirely responsible for the operation of the services they provide. Organizations have complete control over the resources, and they have complete control over the security of their data and their resources. Then you have hybrid clouds. Hybrid clouds combines both public and private clouds, allowing you to run your applications in the most appropriate location. So this increases the flexibility with how a hybrid cloud setup. An organization can determine whether to run their applications in a private cloud or in a public cloud. And it also allows organizations to comply, to adhere to strict security compliance or legal requirements. So now with the Protection of Personal Information Act that's come into being popular, it's very important for companies to protect their clients' information, okay, and to ensure that it's locally stored and not stored in out of the country. So it allows organizations to utilize certain aspects, so that if they can anonymize the data, they can send this data to out of the country or to a region, a cloud region, and analyze that anonymized data and bring it back for their reporting purposes, but they cannot, or their, their marketing purposes, but they cannot send private information, their clients' private information out of the country. So the hybrid cloud allows that flexibility and the compliance in storing the data. So what are the key concepts? So cloud services, okay, offer high availability, scalability. It's elastic and agile, so you can rapidly change it, okay? It's fault tolerant. You can use it for disaster recovery purposes. It has global reach because public cloud vendors have a global reach, okay? Your customer latency capabilities increase. They don't have to wait for a long time because it's an operational expense. You can, to a certain extent, predict cost considerations, okay, if you do your planning correctly. And these companies, these cloud vendors also, they have large IT departments that focus on security. So you can benefit from that as opposed to having your own internal security team, which unless you have the resources to have a large security team, you're not going to have always be aware of what's currently the best practice in security. So you can benefit to a certain extent from that. So they also offer economies of scale because it's able to do things less expensively and more efficiently. And these are large businesses, and they can leverage the benefits of economies of scale and then pass these benefits on to their customers. Now, I'm under no, illusions. All these companies are profit-driven companies, so they also need to they also obviously in it to also generate profit for themselves. So when you utilize them, okay, does it make sense? It's like for mutual benefit. So if you want to start your own company or something like that, and you don't want to invest in that initial capital expenditure, then it makes sense to utilize their services because it can offer mutual benefit. But be under no illusion that these companies are also trying to make a profit. So they're going to charge you. And when we get to the machine learning studio environment, okay, it's important that you switch off or you stop running any compute resource once you finished using it, so that you limit your expenses. So you must just keep that in mind. Otherwise, you're going to be charged large amounts of money. So be very mindful. Delete things, delete anything that you're going to store if you're not going to utilize it. So I've created some stuff specifically around the lecture. And once I'm done, I'll go and delete everything. So I don't store information if I'm no longer going to use it. And I stop my compute instances if I'm not going to use it, because I'm trying to limit my operational expenditure of any services I'm using on the cloud. Okay, so to get the benefits from these vendors is just use them when required, and then stop using it, stop using the service, so you don't continue to pay. Okay, so the benefits also from a company perspective is you're not spending money on physical infrastructure upfront, and a lot of young people are looking at not always just going into a company and finding work, but starting their own companies. Okay, so if you one of those type of individuals who want to be an entrepreneur, this will enable you because there's no upfront cost. Okay, that you just spend money on services and products, so you only spend on operational expenditure, and you are billed for them immediately. Okay, so then you can also, you know, typically if you buy in a business, if you buy something as capital expenditure, you have to depreciate it over a period of 3 to 5 years. Whereas your operational expenditure in the current year that you're spending, it's a liability, so it comes off, okay, as a liability in the year that you're spending the money. So it's more efficient in that sense. Now, this basically shows you the 3 abstraction layers, okay? So traditional, you had everything self-managed by the company. Okay, then we had the initial, you know, certain vendors started saying, okay, we'll manage the data center for you. And then the companies outsourced their data centers to a third-party vendor. And then you had the internet companies that came through and said, okay, we'll do your data center, network storage, and your physical service. And these were your web hosting companies. And now you have your cloud companies, which offer your infrastructure as a service model, your platform as a service model, and your software. And software as a service is you only own the data. Everything else is managed by the cloud provider. So basically, the advantages of cloud computing, it's obviously the financial benefit, okay, that end users share a large pool of storage and computing resources rather than managing and owning their own systems, because it's not just the initial capital expenditure of buying the hardware and buying the software that you're going to install on the hardware. It's also, you have to employ resources to look after these systems. So you'll have to employ, you know, an IT person to look after your resources. But if you say a chef catering, running a catering business, and your focus, the focus of your business is on designing and developing delicious food items, it's not an IT requirement. So if traditionally, if you have to employ someone just to handle your IT, it doesn't make sense to the core focus of your business. Whereas with outsourcing it to a cloud provider, you just use their services and You don't have to, manage the hardware, the software, or another resource employer. So cloud service providers invest in necessary infrastructure and management systems, and in return receive a time-based or usage-based fee from end users. It's emerging today as a commercial infrastructure that eliminates the need for maintaining expensive computing hardware. Through this virtualization, okay, so they promise to address the same shared set of physical resources to a large user base with different needs. Now, from a researcher perspective, scientists traditionally used supercomputers, but now we can use the cloud, okay, for our analytics to store our data and to analyze the data. So we no longer have this in-house requirement for supercomputers. Cloud computing systems fundamentally provides access to large pools of data and computational resources through a variety of interfaces. And here, this briefly shows you the different models. So you have your infrastructure as a service. Okay, it's more flexible because you still maintain significant control, okay, over your software and your applications. But if you just want to keep control over your data, you can go for the software as a service model, which is pay as you go pricing model. Okay, and if you look at this management responsibilities, you have your data governance, your client endpoints, and your account and access management for software as a service, which you are responsible for. Duly between the customer and the cloud service vendor, so in this case, Microsoft, they'll use typically some of the systems available from Microsoft for their security requirements, identity and directory infrastructure, and the rest of it is managed by the cloud service provider, the vendor. So before we talk about Azure, let's just get a bit of historical context. Microsoft entered the cloud infrastructure as a service market, the launch of Azure Virtual Machines in June 2012. Okay. And they offered Hyper-V virtualized multi-tenant compute, okay, along with multi-tenant storage. Okay, and this evolved into platform as a service capabilities and blob storage. And now you have these container service and then even serverless computing with Azure Functions. And as Azure evolved, you had third-party software and service providers offering their applications to be hosted on the Microsoft cloud. And these third-party software and services are available on the Azure marketplace. So I initially intended to have a break at just before I start with the machine learning module. It's now 10:30. Does anyone want to break or can I continue? It's just a few more slides. I know I've been going for about almost 90 minutes, but if y'all can bear with me, I'm going, I just have a few more slides and then we have got a scheduled break of about 5 minutes before I start with the Azure Machine Learning section. I just want to go over the core Azure services, okay? So you'll get a sense of what Azure is, because you'll see when I start going into the Azure environment, you need to understand what your location is, your region is, etc. So I'm just going to give you all briefly about what the core Azure services are. So Azure is made up of global data centers located and organized by country or region. A region is a geographical area containing at least one or more data centers that are in close proximity and networked together with low latency network. Each Azure region is paired with another region within the same geography. Okay, this is for reliability and availability requirements. And this approach allows for the application of resources, okay, across a geography that helps reduce the likelihood of interruptions due to events such as natural disasters, power outages, or physical network outages affecting both regions at once. So you have a geography, which is a discrete market containing 2 or more regions that preserves data residency and compliance boundaries. So currently you have South Africa North and South Africa West, okay, that is within the 2 regions within the geography of South Africa, okay, so it ensures that customers, South African customers, can ensure their data residency and compliance needs, okay. So geographies are broken up into Americas, Europe, Asia, Pacific, Middle East, and Africa. Availability zones are within a region, so physically separate locations within an Azure region. Each availability zone is made up of 1 or more data centers equipped with independence. So this is for your availability requirements. So you'll have multiple data centers in the same region, and they support each other. If one availability zone goes down, these other 2 will still be available. So they set up an isolation boundary. If one availability zone goes down, the other continues working. Other Azure core services are Azure Compute. So this is basically your computing resource, your actual CPU and your hardware, your memory, your disk space, okay, and your network and operating systems. So these resources are available on demand and can typically be made available in minutes or even seconds. And you only pay for the resources you use and for as long as you're using them. So you start a compute instance. Once it's running, you do your computation that you require, and then you stop your compute services. These are typically virtual machine services, which are software emulations of physical computers. And you create and use virtual machines in the cloud. You also have application services, which are platform as a service offerings to build, deploy, and scale enterprise-grade web, mobile, and API applications using a fully managed platform. Then you have your serverless functions, which is Azure Functions, concerned only with the code running. So you only pay for the amount of time that actually code runs and not the underlying platform of infrastructure. So it's commonly used in event-driven systems, okay, where you need to perform work in response to an event, timer, or message from another Azure service. And when that work can be completed quickly within seconds or less. So you only pay for that computation time. And you have your storage services, which is obviously what you want to store your data. You'll have structured data that adheres to a schema. So all the data is the same fields or properties. Semi-structured data, okay, so it's less organized, typically the NoSQL. And then you have your unstructured data, okay. So there's no restrictions on the kind of data it can contain. It can be an image, a file, or video content, or even just a PDF document. You have Azure Storage Service, stores files, message tables, and other types of information. Azure Blob Storage is unstructured, okay, so you can store any type of information. Your disk storage provides disks for virtual machines and applications. Your Azure Files offers fully managed file shares in the cloud. And you can, using the standard server message block protocol, you can access it. Then you have archive storage to store information that's rarely accessed. So if you just want to keep it and at a low cost, you want to store this legacy data that possibly you might want to retrieve, okay? You can do it at low cost, but then obviously it's not available in real time. So you pay for that because you'll have to make a request and you might get access to the data after your request within 24 hours. Then you have your database systems. we have your Cosmos DB, which is a distributed database. You have a SQL database, okay, which is a relational database, is a database as a service. Remember, I said X is anything as a service. A DAS is a database as a service, okay? And then you have database migration service, which allows you to migrate data from your in-house databases to the Azure data platforms with minimum downtime. Some Azure big data analytical services include your SQL data warehouse to store large amounts of data, so petabytes of data. You can have the Azure HD Insight, okay, which allows you to run open source frameworks and create cluster types. So you can use these open source frameworks such as Apache Hadoop, Apache Kafka, the message streaming, queuing and streaming application, okay? And you can have Azure Data Lakes, which is an on-demand analytics job service. And then you have some Azure AI services. And this is what we're going to focus on. Your Azure Machine Learning Service, which provides a cloud-based environment you can use to develop, train, test, deploy, manage, and track machine learning models. Azure Machine Learning can auto-generate a model and auto-tune it for you. Okay, it will start training on your local machine and then scale out to the cloud. And you will also have Azure Machine Learning Studio, which is a collaborative drag and drop visual workplace where you can build, test, and deploy machine learning solutions without needing to write code. So I'm going to give you all a brief demonstration of that. And like I said, I'm not a data scientist. I'm also learning because we have a requirement in our research for certain machine learning tools. And that's what motivated me to learn about these Azure services. I'd worked in the corporate environment with the Azure IoT Hub, which is their Internet of Things hub. And I'd use their Azure storage services to store the information retrieved from these sensors. But I hadn't really worked with their AI functionality until my research requirements led me to say that I'm going to have a need for understanding how the Azure machine learning tools can assist me, because like I said, I'm not a data scientist, so I don't have that background of using these tools on their own without having to spend a lot of time and effort in installing it and getting up to usability stage. I just wanted to try certain ideas out. So it's good for experimentation. And if you don't want to spend a lot of time getting your whole data science environment up and running, it's very useful for that sort of environment. Okay. So I'm going to give a brief break now before we go into the machine learning platform. I think we can take a 5-minute break. Okay, so I'm just going to stop sharing now and I'll be back in 5 minutes. Thanks everyone for sticking around. We will resume it's 10:42. We will resume at 10:47. And then we're going to look at the Azure Machine Learning Studio. Okay, welcome back, everyone. I'm just going to reshare my screen. I'm going to. I just want to send everyone a link that I think is going to be useful. I'm going to share this link. The chat group. Okay. So I've posted a link on the chat group for the Microsoft Learn environment. Okay. And you can learn there's a lot of information. So it's entirely up to you. There's so much information available now that it becomes almost your responsibility to structure your learning journey and how much effort and time you want to invest in your self-learning, so that you depends on what you learn. So you can learn anything. There's different modules where you can learn an overview of Azure Fundamentals, or you can focus specifically on the machine learning aspects of it. And we are going to go through one of those learning modules to work through the Machine Learning Studio environment as an example. Your portal. So as students, if some of you are currently registered as students, okay, then you have access to, or if you've never used the Azure portal before, okay, you can get a complimentary $200 for a year subscription. On the first time you use Azure, okay, thereafter you have to obviously pay for the service. And then if you're a student, you have access to the machine learning portal of about $100, but you have to verify that you're actually a student, or if you work for an academic type institution, so a school learner, or you actually work for a university or tertiary education institute. And then you get about $100 free access to the machine learning environment. Okay, so I urge you to go and open up a subscription and play around in the portal, and you can access it. So data scientists, they expend a lot of effort exploring and pre-processing data and trying various types of model training algorithms to produce accurate models, okay, which is time consuming and often makes inefficient use of expensive compute hardware. But the Azure Machine Learning, You have a cloud-based platform for building and operating machine learning solutions in Azure. It includes a wide range of features and capabilities that help data scientists prepare data, train models, publish predictive services, and monitor their usage. Most importantly, it helps data scientists increase their efficiency by automating many of the time-consuming tasks associated with training models, and it enables them to use cloud-based compute resources that scale effectively to handle large volumes of data while incurring costs only when actually used. The Machine Learning Studio is a cloud-based environment you can use to train, deploy, automate, and manage and track ML models. And Azure Machine Learning can be used on any kind of machine learning. It's a polyglot environment, so you can use different types of programming languages, okay, to build, train, and track your resources, and you can have access to it at that stage. I just want to toggle. So I'm going to stop sharing and see if I can share my entire desktop, because I just need Cherise or someone else. I'm going to try to share my entire desktop, and I'm going to toggle. Can you see now my Google screen? Can everyone see? Okay, excellent.
We can see it. Thanks, Suvendi.
Okay, thank you. So this is what a typical Azure portal would look like. Okay, so if you go at portal, okay, when you log in, this is your Azure portal. This will be your who you are, okay? So you'll see that information. You can get help, your settings, your notifications, and this is your terminal or cloud shell information. Then you'll have a dashboard and you can see your resources, etc. Okay, so this is going to be your typical Azure portal from that web link. Okay. And this is a typical when you go into the Learn environment. So you can, there's every different modules where you can learn. So here it's the Azure Fundamentals. Okay, so you learn about basic cloud concepts, and then you can do a search. So you can say search machine learning, okay, and you can, so I'm just going to go for straight machine learning as opposed to studio or other sort of information. And then you'll see there's different, so there'll be different aspects that you can learn. Okay, so you can choose anything and you can go through it. And I really recommend, because I've been doing this, not all the time, because there's other things, as you can see. I've got lots of things. So I'm a bit of a dabbler. And when the need arises in my research to learn something, then I try to learn it so that my research can progress. But I really encourage you to make use of this free resource to increase your learning. So this is your Azure portal. Okay, this is just an example of what it looks like. And then to create a machine learning resource. Okay, so I'm just going to go here. Okay, let me go to this one. Okay, and if you want to, you can you'll see I've created already a workspace resource. Okay, so you can find you can go to home. Okay, and then you can go to create resource. You can type in machine learning, enter. And you'll see there's a whole variety. So remember I mentioned the Azure Marketplace. Okay, so you'll see some, there's also other vendors that, so here we had SAS. So SAS is an external vendor. So they've got their product on Microsoft Azure Marketplace, okay, that they're offering it. So you can actually use that. So they'll offer all these different vendors can offer their systems. Microsoft, they've got their own internally built machine learning. So this is what we're going to use. So you can click on this for the Microsoft. And then you can, so their Azure Machine Learning, okay, is their inbuilt system that provides for building, training, and deploying machine learning models. And if you click on create, okay, so you can, so like I said, if you as a student or someone employed in a university or tertiary education academic institution, you can have access to the initial $300. You can create a resource group, which if you click on the information, they'll explain, it explains what it is. It's a collection of resources that share the same. So if you want to put all your the resources, the Azure resources you're going to utilize. So if you're going to have a storage account, a key vault, so all in one resource group. So you can create a resource group that I'm going to, whatever you want to name it, you can create your workspace name. Okay, so you give it a unique name. You just click on in this stuff, so it's unique. Remember, we talked about regions. Now, if you look at regions, these are the regions currently where this machine learning is available. So it's available in Australia, Brazil, Canada, East Asia, France, the US, and the UK. Notice Africa, although there's Azure, Africa, North and Africa West in South Africa, they haven't made the machine learning service available. So not all services are available. Although we have an Azure region, we don't yet have all the services available. So we'll have to choose something else. And my default is to choose West Europe, because in terms of time, we are on the same longitudinal, so we generally tend to be in the same time zone, etc. Okay, and then once you put in your workspace name, okay, which is a unique workspace name, it will create a default storage account. Okay, so your storage account is used as your default data store for the workspace. You have a unique key vault. Okay, so it's used to store your passwords, your secrets, and other sensitive information. Application insights is to show how you're using your information. So it's it's the same way as you go to any website. It's storing how you're interacting with that website. So this to store how you're interacting with the application, and then you have a container registry. Because I'm not going to show you how to deploy the application, because that's part of more of, if you're in a corporate environment trying to sell access to your data science algorithms, then you might want to deploy your data science algorithm model as a web link, and have other third parties come to that web link to enter in data and get a response. Okay, but we're not going to look at that specifically now. So this is what you typically enter information, and you'd say, okay, your networking, and then you can say review and create. Okay, I'm not going to do another machine learning workspace, because I've already got a machine learning workspace, but I've just taken you through the steps. You can rename this. So you can rename, you don't need to use the default name, you can use something else. Okay, so you can use a different name. You're not restricted to this name. Okay. So I'm not going to go through this specific. I just wanted to go through how do you create your initial machine learning workspace. And then you say review and create, and it will take some time to review and create it. Okay, once it's created, you'll go into this environment, and this will be your machine learning workspace. Okay. And you can go into overview, your activity log. Remember what I said, it takes, so for efficient use of your account, make sure as soon as I'm done today, I'm going to delete it. And when I need another machine learning workspace for that brief time, I'll go and create it and create a compute resource, and then utilize it, and then I'll delete it. So that's how I optimize my monetary value. I don't keep things indefinitely, because it uses a tiny amount of storage, but that all adds up, and it is being calculated in dollars. So it does add up. So just be aware of when you're using your when you create an Azure environment and you utilize any of the services, you keep in mind that as soon as you finish use a service, stop it, delete it, so it doesn't cost you anything. Okay, so just be aware of that. So this, I just took you through the steps. So you go here into the create resource environment, you search for machine learning, and then you saw this environment, the marketplace. It helps connect end users with Microsoft partners, independent software vendors, and startups that are offering their solutions and services. Okay, and it's mostly for IT professionals and cloud developers to try, purchase, and provision applications. And then we chose that, and we could fill in all this information, and then you just say review and create, and it will take a few minutes to create your workspace. And once you've created your workspace, okay, then you can launch your Azure Machine Learning Studio. Okay, so you can either from your workspace go and launch your Azure Machine Learning Studio, or you can navigate to, so just remember we went to https portal azure.com. I'll just go back to that slide. See, it's portal azure.com. Okay, and in the portal, you said create a resource, and you created your machine learning workspace. Once you've created your machine learning workspace, you then go to ml.azure.com, or from your machine learning workspace, you launch your Azure Machine Learning Studio. Okay. So this is my machine learning workspace. Okay, I was just showing you the different aspects to it. Okay, your tasks, you get some alerts. So we'll go back to overview. And we'll go and say, launch Studio. Okay, so this is your Azure Machine Learning Studio environment. Okay, so this is similar to what I've just shown you. So this is your Azure Machine Learning Studio environment. So within your workspace, you have your authoring, okay, which is your notebooks, your automated machine learning and designers. So this is for building, training, evaluating, and deploying machine learning models using an authoring tool. Then you have your assets, which are your data sets, your experiments, your pipelines, your models, and your endpoints. And this is where you prepare your data, run and monitor your jobs, view and deploy models, manage real-time and pipeline endpoints. Then you have your management, where you can view and manage resources for your workspace. And at the top, you have help, you have feedback, and then you can pick your workspace. So this is your workspace. These are your authoring tools. These are your assets. And this is your compute environment. This is help. This is feedback. And this is where you can select your workspace. So if you've got multiple machine learning workspaces created, you can choose which one you want to use. Okay. If you go to compute, okay. I'm just going to, while I'm discussing this, I'm going to start this because it takes some time. And I stopped it so I don't waste money unnecessarily. So you have different types of compute. Okay. I'm going to discuss that briefly. So you need to create a compute instance. Compute targets are cloud-based. It's actually your hardware. It's your little computer, okay, that you're going to use to run your models and your data process exploration processes. So it's a cloud-based resource which can run model training and data exploration processes. To run a notebook, you will need a compute instance in your Azure Machine Learning workspace. In Azure Machine Learning Studio, you view the compute page under Manage. Okay, so we went to Manage area. Remember, this is your Manage area, the management, compute, environments, data stores. And you clicked on the compute link and you saw your compute page. And there we saw our compute instances, clusters, inference clusters, and attached computes. This is where you manage the compute targets for your data science activities. There are 4 kinds of compute resources you can create: compute instances, which are development workstations that data scientists can use to work with data and models. And you have compute clusters, which are scalable clusters of virtual machines for on-demand processing of experiment code. You have your inference clusters, which are deployment targets for predictive services that use your trained virtual models. And then you have your attached compute, where you can link to virtual machines or Azure Databricks clusters. Okay, so today we're going to use compute instances and compute clusters. So my compute instance I've already created. I'll take you through the process of creating a compute instance, and I've already created a compute cluster. Okay. So you need to create a compute instance. On the compute instances tab, okay, you can say a new compute instance, and typically you'll set it up. So you're going to choose CPU, unless you really require the additional processing capability of a GPU. So if you go here and you say new, okay, you enter in your compute name. So if you click on the little I, it tells you the requirements for your compute name. It must be between 3 to 24 characters long. It can have only valid characters, the upper and lowercase digits, and the minus character. Okay, so you cannot have any other type of characters. It must start with a letter. It must be unique across all existing computes within an Azure region. And if this character, if the minus character is used, then a dash character, then it needs to be followed by at least one letter later in the name. Okay, so this is the requirements when you create a compute name. The location, okay. So the compute instance is always created in the same location as your machine learning workspace. So I created my machine learning workspace in West Europe. So my compute instance will also be created there. Okay. So you can have GPU or CPU virtual machine types. When using GPU-enabled virtual machines, make sure your code is written to leverage available GPU devices. Okay. You can also have different virtual machine sizes. So you can see which are the virtual, the full list of virtual machine sizes. Okay. And so the standard when you virtual machine size that you can use is this. Okay, it's also not that expensive. You can see this is cheaper. Okay, but it's this says 14 gigabits. This is only 3.5. Okay, so and this is 2 cores. So you have to decide as you're a data scientist which virtual machine you want to use. But this is normally the standard one that is typically used, and it's suitable for most type of applications. Okay, so it's the optimal balance of cost and performance. Okay, you have to enter a unique name and just leave access unselected, and then you can create. It takes a couple of minutes to create. It's important to stop your compute instance to avoid incurring unnecessary charges to your Azure subscription. So once you finish use it, you can stop it. So because I haven't entered in a compute name, it's not going to go. Okay. And if you go to next advanced settings, just leave it as default, and then you click create. I'm not going to create because I don't need it, and it's just going to cost me money. I've already got a compute instance. I'm just walking you through the process of how you'd create a compute instance, okay? And the typical virtual machine that you'd use. Okay, so I've already got a compute instance. There's also compute clusters, okay? You can then also create a new compute cluster, very similar, okay? You choose your location, okay? It's dedicated CPU, and then you choose. So always say select from all options so you can get more variety, and you can see, which sometimes recommended is not always in your best. And then you can choose, generally this is the standard, and it's also relatively inexpensive usage. And then you go here, you enter in a name for your compute cluster. Okay, minimum number of nodes, maximum number of nodes. You can just make it 2, depending on your requirements. You'd want to make that lower, so maybe just 2 minutes, okay? And then as opposed to 30 minutes, that normally do. And then you can create. You can say create, and you create your cluster. So I'm going to cancel because I've already created a cluster. Okay. I'm just going to take you through this quickly. So this is typically, it's like I said, the balance. So your choice of virtual machine size depends on your current requirements. Okay. So you create this. Now, once you've created your compute environment, okay. This is your compute cluster. You can see it. Go back to your compute instance. Okay. You click on this. It's already got these applications installed on the compute environment. So it's already installed a typical notebook that's used by a lot of data scientists. So you can go to your Jupyter. This is for learners, and I find this very useful as opposed to having to do things from scratch. You can download from GitHub the ML basics notebooks, and you can just use it. So if you open one of their basics, it gives you good background on the particular ML type technique that they're discussing. And you'll see that it includes not just the actual data, but it also descriptions. So it's very useful as a learning tool. Okay, so download from GitHub. I'll post the link later that you can go to GitHub and download the files, and you can just access it, these Jupyter notebooks, so it will also be useful. And then you're all familiar with how to run your notebook, and you can just see this. So this is, you can create a notebook and you can run it. The nice thing about it is you don't have to then go and install Python and then or Anaconda and then say, okay, I've got the right version of Python, and the environment ensures that you've up to date with the latest version of Python, and that's supported, and your notebook will run in that environment. So you're not responsible for setting up your machine learning environment. It just supports it by default for you.
Prof, there's a question in the chat. I'll read it out to you. Menzi is asking, what is the advantage of Azure over Python when it comes to machine learning?
Azure is not a programming language. Okay, Python is a programming language. Azure is a group of cloud services. Okay, so it's multiple different types of technologies. It's a name for it's a business name. Okay, for a group of IT services that's offered by a company called Microsoft. Okay, and this IT services could be actual compute instances offered as infrastructure, so it's virtual machines, or it could be one of the services they offer, Microsoft offers, is machine learning, okay, where you can go and, as I've shown you, create a compute instance, and then currently, we're running a notebook on this compute instance that was created, and you can utilize, in the notebook, because it's Jupyter, you can utilize Python. Python is a programming language. Azure is not a programming language. It's a service offering from Microsoft of a whole lot of different IT services. I hope, Minzy, I've answered your question. Okay. So it's not like you're comparing R and Python, okay, for machine learning, and to say which is the better, or Octave and MATLAB to say which is better for machine learning. Okay. So I'm going back to the studio. Okay. Now, so I talked about this, and I gave you all, you can run your Jupyter notebook in an Azure Machine Learning Workspace. The setup ensures the correct version of Python, and the various packages you will need are installed. And after creating the workspace once, you can reuse it in other modules. Now, I want to talk about the regression example I'd like to work through. So the reason I chose this is, as I explained, I'm not a data scientist, and I'm also still in the process of learning the different aspects of the tools that I need that will assist me in my research. Okay, so this is typically used for prediction, and I thought it's one of the relatively easy and less complex type of machine learning techniques, and it will be good for an introduction to the Azure Machine Learning Studio to use it as a demonstration example. So I'm going to post this link on the website. Let me just go back to right at the beginning. And then you can actually follow from here. I'll post this link. Okay, so we're going to go through this machine learning example, where the first step would be to create a machine learning workspace, which we've already done. Okay. So we're going to use the workspace I've created. And I've taken you all through this, the basic steps where you have to specify your resource group, your workspace name, etc. And then once you've created your machine learning workspace, you create your compute resources. So I've already created a compute instance and I've created my compute cluster because it takes some time. And then we'll go to the step now where we go to explore the data. Okay, so you can add and explore a data set. So we have to create a pipeline. So in the Machine Learning Studio, you have to create a pipeline. Okay, so we go here, we go to Designer. Okay, and you're going to create a pipeline. So I'm going to say new pipeline. Okay, and you'll see I need to select my compute target. Okay, so this is the compute cluster. That's my compute target that I've selected. Okay. So in Azure, you go to the designer page, okay, which is what I did. And then I said, create a new pipeline. Okay. So then I change my pipeline to a specific name, okay, which I'll do. And then you need to specify your compute target. Okay, so that's what I did. Okay. I'll specify my name just now. And then you have to create, in the designer, you have to go to the sample data sets and use the data set. Oh, if you create your own data set, okay, then you can upload the data set either in tab separated or comma separated values and create your own data set that you can import. Okay, so this one. Okay. Here's your data sets. That you can use, and then you have your sample data sets. Okay, this is the sample data set that you're going to use. Okay, and if you right click, you can go and preview the data. Okay, so you can see So this is the different types of columns that's currently in this data. So if you look here, yesterday, Prof. Leke was talking about missing data, and you can see this column here has got a lot of missing values, okay? This column has got no missing values, no missing values, missing values, no missing values, no missing values, no missing values. Okay, here we've got 4 missing values under the ball. Field system has got no missing values. Stroke has got 4 missing values, no missing values, 2 missing values, 2 missing values, and then no missing values, no missing values. But if you look, the difference between like here, which is in the 5,000, okay, is the data value, and price, which is in the 10,000 price range, and then you have compression ratio and stuff. So you also have to normalize your data. Okay. So we've added in a data set. So we've gone and added in automobile price data, okay? And we've looked at some of the values and around that price data, okay? Now we need to add our data transformation. So we need to transform this data so we can ignore the missing values and we can normalize this data, okay? So we go into the data transformation section, okay? And we're going to say select columns in the data set. So we're going to go here, and that's my data transformation section. And we're going to look for select columns in data set. So we're going to scroll through these values. Select columns in data set. Okay. And I want to select columns that I want to transform. So I'm going to go here and I'm going to say edit column. Okay. I can say select columns. Okay. Or I can say select by name. So go. Save. Connect. So connecting just does that. I'll say save again. And I'll say edit column. And then I can do by name. Okay. Now I want to add all the columns except now normalized losses, which had a lot of missing data. So that's going to impact my analysis with a lot of missing data. So the rest of the columns had just maybe possibly 0 missing data or maximum 4 rows that it was missing. Whereas this one had 41 out of 51 rows that was missing data. So I want to ignore this. So I'm going to say add all, and then I'm going to say remove. Okay. And I'm going to say save. So I'm going to select all the columns except for normalized losses. Okay. So here, you select all the columns other than the normalized losses. I hope if y'all, I posted the link so y'all can follow through, y'all can go to that link and y'all can follow the read through. I'm not going to spend a lot of time reading through it. I'm just going to show you all the process. Okay, so in the rest, you're going to create a pipeline where you're going to say clean missing data and then normalize data. So this is the steps we're going to follow. I urge you all to actually go to the link so you all can read through the steps. I'm not going to spend a lot of time reading through the steps with you. I'm just going to show you all the process. Okay, and then so we're going to now follow this step here, which is the clean missing data, and we're going to take it from the data transformation section, and we're going to place it under that section. And we're going to say the clean missing data is bore, stroke, and horsepower. Okay, because those were the three columns that had missing data. Okay. So we're still under data transformations. So we should get clean missing data. So it's alphabetically ordered. So we should come to here, clean missing data. Okay. Link it. Save it. Edit column. Okay. And we look for bore. And we look for stroke. Look for horsepower. Then we say save. Okay. So we've done this section here, which is columns to be cleaned. And we've put the three columns that we want to be cleaned. Now we also want to say minimum missing value ratio is 0, it's 1, and the cleaning mode is remove entire row. So they generally default values except for the cleaning mode. So it's 0, it's 1, okay, and it's remove entire row. Okay, then we're going to say normalize because we have different values. So we need to normalize this data. Okay, so after we've cleaned the data, we need to normalize the data. So we'll drag a normalized data module to below the clean missing data module. Okay, and then we connect the leftmost output from the clean missing data module to the normalized data module. So let's go and get a normalized data module. Here's normalized data. Okay, now if you go and hover here, you'll see the leftmost of clean missing data output says cleaned data set, data frame directory, and the rightmost says cleaning transformation. So the different outputs from clean missing data gives, if you go and hover over it, it tells you what sort of output it's intended for. So this is a cleaning transformation, and this is the cleaned data set. Since we only want the clean data set, which is just the removal of that missing data, okay, we go here and we want to normalize that. So that becomes our input data. Okay. And now we need to set up our normalized data module. So in this, we can view its settings, okay? And we set the transformation to min, max, and edit the columns, okay? So we choose these columns and we add a rule to this columns. Okay. So I'm going to choose min, max. Yeah. Edit column. Now, if you look here, there's a lot. It's symboling wheelbase length and width. Yeah. Symboling wheelbase length. Height, curb weight, engine size. Oh, it's bore, not horsepower. So I take away, put in bore. Horsepower. I say. Okay. And then, oops, there was also these. So it's stroke, compression ratio, horsepower. I need to add in edit column. I've got all the data. If you've noticed that I've missed some of the data, please speak up so I can go and edit. It's going to affect the result. So if you've noticed that I've missed any of the data, please let me know. Okay, then we run the pipeline. So my pipeline should look like this, and then I'm going to submit, and then it will take some time. So this takes some time to run. Checked everything, looks normal. What you can do is you can ask year to, and then it will set up to look quite neater. Okay, and then you can just move it a bit up here if you want. So it looks a bit neater. Then you can say submit. Okay. And you can either select existing or create a new training. So if you want to create new, you can say And you can say submit. And then it will run. And you can go to run overview and it will tell you. They say normally it takes about 5 minutes. And then you can go to attributes and it will tell you so far it's only been running for 4 seconds and this will update continuously. Okay. That it will tell you. Okay. Run over. So here my run is finished. Okay. And you can see I've got green for the select columns in data set. Clean missing data. And the normalized data. They're all green. So that's run relatively fast. Okay. Save this. So I've done this section. Okay, so I've set my data. I've selected the columns I want to work with. I've cleaned the missing data and then I've normalized the data. So I've basically completed the transformation aspect of my data. Okay, so now it's ready to be, okay, the data set is now prepared for model training. So we can just look at the output of the normalized data and then we can go to the next step. Much of my okay. So we can go here and we can visualize it. Okay. And we can see we no longer have the normalized losses and all the data has been normalized. So given, okay, except for price, because we didn't include price. Remember, we didn't include price in the normalized data, but everything else has been normalized. Peak RPM, power, etc. So that's our output data. Now we go to create and run a training pipeline. So again, this is what data scientists would typically do, where they'd create a certain percentage of the data, okay, to train the model, and another percentage of the data to test the trained model. So this is what we're going to do in the next step. We're going to split our data, and then we're going to train the model, and then we're going to score the model. Okay, let me just go here. So let's go and implement this section. Data transformations, we go and get the split data module. We connect it to the normalized data. And then we set up this in our module. So let me just go here. Split data module. Now remember, this is the transform data set. And this is the transformation directory, transformation function. So we use the transform data set to our split module. Save. Okay, so we're going to split on rows. Okay, we can make it a 0, 7. One, 2, 3, and false. This is just 1, 2, 3. And this provides a random seed, random number generation seed. So we're just setting it to 1, 2, 3. Okay, not to save. So now we need to train the model. So we can drag a train model module to the canvas. And we're going to connect the result data set of the split data module to the train module. Okay. I'm just going like this because for some reason this doesn't want to disappear. It used to disappear and now it's not disappearing. So sorry. Sometimes you just have to do this so that it makes it easier to move. So you ask a default to set it up, and then you can move your data rows. It creates more space for you by default. Okay. So I go to model training. And I want to put train model here. So the results data set goes to my train model. There's two of them. So the data set, data frame directory, and the untrained model. Okay, so we want to connect this data set to the train model. Okay. So we need to set the label column to price because it's trying to predict the price. Okay. Save. Notice it's no longer got that warning sign because I've now added price. So it's fine. Okay, so if you select the way I've been selecting, you don't need to worry about the case and spelling. So if you type it in, that's when you have to worry about, okay, you've got the correct case and spelling, but if you just select it from the columns, it's a bit more time consuming, that process that I was following, but then you don't have to worry about the spelling and making a spelling mistake. Okay. So then we need to go to the machine learning algorithm section and under regression, drag the linear regression module to the canvas. So this is the linear regression that we're going to be using. Okay. But here it's going to be to the left of the split data module and above the train module. So the linear regression, okay, is to the left of the split data and above the train module. Go here. And I'll go here. There's my linear regression module. Okay. I'm going to put it here. Like this to my train module. Same. Okay, so I've connected that, connected that. Then we need to test the trained model. So we need to score the validation data set. Okay, so this is the missing 0.3, okay, of the data set, the 30% that when we split the original data. So we need to include a model scoring and evaluation section. So we need to include a score model below the train model module. Okay, so I'm going to include a score model that comes from the model scoring and evaluation section. Let's increase this. it's going to say what to set up, because it helps. But in this particular aspect, let's go to sorry, keep on pressing on the wrong thing. Scoring and evaluation. This is the score model. So I just want to make space for my model to come here. So it's got two inputs. Just going to show you all the two inputs. Okay. This is your data set. Okay. And this is the trained model that needs to be connected. So I'm going to connect the trained model to here. And this is the results data set to there. Save. So we're going to say the score model, we've connected it. Okay, and connect the output of the train model on the left, the score model, and the split data to the score model like this. So we can confirm that I've set it up correctly by going back. Let's see that I've set it up. Looks correct. Okay. And then you just run the pipeline. And then you say submit. It takes a few minutes. And then once it's done, it's completed, you can go to the score model and look at the visualize icon. Okay, and then you'll see the scored labels. Okay, and you can then evaluate your regression model. Okay. I'm just going to go back and say submit to run my pipeline, because we ran our pipeline till here, so it's green. So we still need to run the pipeline for the remaining modules that we added to see that it's working correctly. So I'm going to say submit. Say submit. And it's going to continue to run. Okay. You can see it's green here, green, green, green. And the score module is green. So if I say auto layout, it will just rearrange my data into a neater format and to allow me to scroll a bit. So I'm just, the reason I do the auto layout every now and then is that it creates more space for me to play around with my modules. Otherwise it just restricts the space. Okay. Go to score module, output logs. And then I can say preview the data, which is the visualization. Okay, I can increase this. And I can see, so I can go here. I can go to scored labels. Okay, I can see the information and I can go to price. See the information. So So here they say we can visualize the results and we can see the price column, and there's also a scored labels that contains the predicted label values. Okay, so we can see that in our score model result. Now we need to evaluate. So we've got the model up to predicting the price label, but we need to evaluate how reliable its predictions are. So in order to that, we need to evaluate the regression module. Okay, so we evaluate a regression model. So we go to this step. We've up to here, the score, then we add and evaluate model selection. So under model in scoring, there's an evaluate model module to the canvas. Okay. Back instead of just closing it. There goes my way to score. Okay. So this is the score data set, and this is the score data set to compare. Okay, so I'm going to connect this to the score for the score data set. So then they say submit, and then you just, once it's done, select the evaluate model, look at the visualized. Then we're going to see the different errors. So let's go back here. Say submit. Okay. So we can see the different computation. So although this looks good, okay, and this is close to 0, but if you look at this, these values are quite high, which is not so good. So obviously our regression model is not so great. So we can experiment with different types of models until we find one that's suitable. Okay. So here they just briefly explain about the different types of errors. Okay, they say, they give you an explanation what your results are of this evaluate model. So this, the mean absolute error shows the average difference between predicted values and true values. The root mean square error, which is the most familiar, I think, of all that most people know. And this, you know, it's a large value, so it indicates greater variance in individual errors. Then you have the relative squared error, and this is generally between 0 and 1. Then the relative absolute error, and then the coefficient or R squared value. Okay, so that's your model visualization window, and that's typically how you'd create in the Visual Studio without writing any code. Okay, you'd be able to add a data set, clean the data. We did it in a practically about, I think just, and this was myself trying to explain. So it's easily achievable in about an hour, where you could, go through this process and run it, get results, and say, okay, your regression model is not so great, and you'd want to change it and to a different regression model, or run it a different experiment. And then you could say, okay, this is useful or not from what I require, and you could adapt it. But it's entirely possible without writing any code. You can test. Okay, so you can add data sets. You can do your, so there's inbuilt data sets that Microsoft provides. You can have experiments that you can run. So these, and then obviously the pipelines which we created, okay, different models, okay, that you can create. And so these are, obviously these are your data stores that you can use, different data stores. And obviously you can create new pipelines. It's important to remember to delete everything you created once you finish using it. Any questions from anyone? Thank you for, it's way past 12 o'clock, so thank you for staying with me, those who are still around. And I hope it was useful for the information that I've shared. Thank you, everyone.
Thank you very much, Prof. Are there any questions or any comments at this point? All right, I think, yeah, Prof, I think you've answered all the questions that, that everybody had. At this point, I just want to thank you very much for your presentation. It was extremely informative and I think extremely useful. And in general, I also just want to thank all of our speakers and the participants. I'm hoping that we can have another winter school next year, and COVID permitting, actually do so in person, so that the practicals that you've had, you can actually can form a part of the student workshop and you can do it in person. So additionally, for those that are interested, we are hosting a postgraduate workshop in December. I've provided the link in the chat for those that are interested. and it's going to be focused on machine learning in particular. So thank you very much, everyone, and have a lovely weekend.